actually dive into the process of creating a learning model. So now a learning model is going to be created with PyTorch. We are actually going to utilize OOP. And we will build two methods. One, the init method, which specifies each layer of the neural network. And two, the forward method, which specifies, and I'm just going to say controls, how data is fed through the layers of the neural network. All right. Well, what is a neural network? We're taking a look at this picture a couple of times, and that's great. But what exactly does this mean? Well, we have an input layer, a hidden layer, an activation layer, and an output layer. Now, all of these layers are essentially something called linear layers. Let me see if I could fill this out and then linear. Okay. I'd be doing it if I do it this way. Here's the documentation for the linear function. This linear function is very popular as far as to utilize inside of hidden layers. But essentially what it does is it takes in a number of inputs and provides a number of outputs. Well, if we take a look at the drawing here, what we're saying is we're going to take in 1, 2, 3, 4, 5, 6 different features, and we're going to output almost triple the amount. I'm not going to actually count them because there's a lot of neurons, but it's going to essentially create or generate an output of hidden layers. Now, the process that it does for doing this is it utilizes something called weights and biases, where weights mean how much meaning does this one specific input have upon all of the new neurons that I'm about to create. And biases are like the checks of saying, hey, you have too much weight now, you have too much impact on all of the other neurons, so we need to reset you. It's like a penalty, right? It says, all right, well now you've passed, you overdid it, you made yourself too important, so let's go ahead and fix this by making you unimportant. And it essentially just deducts the amount of weight that it has upon the other neurons. All right, so weight is the amount of meaning that it can take upon the next layer, and then bias is the checker, whether it's, hey, you're having too much meaning or you're not having enough meaning. All right, so that's it. Weights, the amount of meaning, bias is the checker. And this process of relating to one another happens at each layer of the neural network. When we're feeding this information in, we're going to feed it in with the current length of the amount of neurons that we have, which in this case, I believe we have 13 features. We'll take a look here shortly. We're going to take a look at the hidden layer. And all the hidden layer is essentially a series of linear layers where we're trying to, at first, open up our neural network, try to create meaningful connections, and then slowly deduct them into our number of possible outputs. We'll cover the activation layer later on. Well, let's take a look at what our neural network could look like with this information. All right, first off, I want to take a look at the number of features that I have. So I'm actually going to come up here and I'm going to just insert a new code block where I'm going to print training features And I'm gonna take a look at the length of it. Oh, that is not a good way of seeing it. Let me come up here. Okay, so there we see 1, 2, 3, 4, 5, 6. There's actually a way it tells me. So there's 13 columns. So we do have 13 features to account for here. All right, great. When I can start creating my neural network, this syntax shouldn't be something outside of the world for us. But if at any point the syntax that I'm utilizing becomes confusing, please stop me and let me know so I can break it down. So we're going to go from torch. I want to import nn, and I'm going to import it as n. I'm then going to create a class. This is going to be my learning model. Kind of like how we made that chatbot. But this class is actually going to inherit. I'm going to create my init method, which will take in self. And then I'm going to create my forward method, which will also take in self. And we will cover what other argument it'll take in here shortly. So again, this class is meant to inherit. Inherits from nn to be identified as a learning model, right? So we want all of the features. We want to inherit everything that is a learning model inside of NN, which stands for neural network. So I'm just going to say n.module. This turns this class into a neural network. Now, because I'm utilizing inheritance and I'm going to want to initialize that inherited object, what kind of method would I need inside of my init method?
Super.
Super. Yeah, I want to actually utilize the super method where I'm going to call the class itself. So learning model, pass in self, and then initialize. Now I am passing in the learning model or this model that I'm creating into n module. So that means that somewhere in the background, there is a class named module that has an emit method that takes in self and then takes in a model, which should be of type module. It's redundant, but that's the way it's essentially breaking down in the background. We're passing it in straight into the learning module. So now our learning model can start specifying neural networks. Again, a neural network has linear layers, where each layer takes in two arguments. Argument at index or first argument will be the amount to take in, and the second argument will be the amount to output. Now, the output could either amplify and or deduct, or amount of neurons. Currently, I'm receiving 13 features. So my very first layer, which I'm going to say layer 1, will be of n.linear, where it's going to receive 13 features. I like to multiply it times 2 and then round. So if it comes out to 26, I would round it up to 30. And then from there, I just like to deduct by 5. I don't like to make drastic deductions. That's just my specific take on it. It's up to you all how you like to change your neural networks around. Some people like to do it within 3 layers. Other individuals like to do it within 5 or 6 layers. But now I want to actually take a look at my possibilities for my targets because my final layer should output the same amount of possible targets. So let's take a look at our data one more time. And what I'm trying to achieve here is what the grade class would be, where grade class is 2, 1, 4, 3. Okay, I'm not seeing any zeros. Okay, there's a 0. So it looks like it's between the options of 0 through 4. So that means there's 5 possible types or 5 possible outputs. So in this case, I would have 5 possible outputs. So I could say self dot layer, and I'm just going to call this layer 5. Why not? And then could make that equal to n linear, where I take in a certain amount of neurons and I will put out 5. All right. Now a visual representation of this, again, we're essentially taking in our features into the neural network. We're then amplifying our neural network. And at each layer, we're going to slowly decrease until we can put out the same amount of possibilities. All right, so in this case, there's 5 possibilities, so that's 5 possibilities that we'll be putting out. Does anyone have any questions regarding the linear layer or how we're designing this learning model? Let's hear it, Tom.
Yeah, could you break down your super again? I get that we're taking in the in-dot module and we need to use the super because we're inheriting from it. Um, but why specifically are we passing in itself?
Yeah, because the class of module in its init method, I try to write it up here. In the class of module inside of its init method, it's expecting to know what the model is that's inheriting the module. So we're passing it as an argument to the init method of module.
Got it. Okay, makes a lot more sense.
Awesome. Any other questions? Okay, in that case, let's continue on our busy work here. We're going to make a new layer. Here, I'll name this one layer 2. I'll say n.linear. And I'm actually going to decrease. I'm going to decrease slowly at first. So I'm going to go down to 25. Again, I'm going to input 30 because that's the amount that I'm putting out from the previous layer. It's 30. And the amount that I'll put out in the next layer will be 25. Self.layer 3 will take n.linear, take in 25, and it could output something like 15. And then finally, I could have self.layer 4, where we have n.linear, take in 15, and output 10. And then on our final layer, our 5th layer, we would take in 10 and output 5. Right, so you'll notice there's a couple of drastic drop there. This is called bottlenecking. And then afterwards, we go back to a slow decrease of the drop. So we increase dramatically and then we slowly decrease. All right, so this specifies all of the different layers. But even though this specifies all the different layers, the forward method is what controls how data is being passed through each layer. Well, the forward method would actually take in an argument named data, which we'll reference to as x, or actually we could reference to as data here. Let's call it features. Here we would just explain that features is essentially equal to self dot layer one, where we pass in features. All right, so this would then return 30. Features is equal to self dot layer two features, which would output 25. Features is equal to self dot layer three features, which again outputs 15. Features is equal to self dot layer four, where we pass in our features. This outputs 10. And then finally, features is equal to self dot layer five features, which outputs are 5. And at the end of it, we could return features themselves. Now, this is able to give me a pretty accurate account. It's going to run through each independent layer, try to learn through its weights and biases, and we're not covering the learning process just yet. We're simply just feeding our neural network all of our data. But again, we're not covering the learning process yet. Now, when it comes time, to actually make a guess, we need to specify this is a type of action that you'll utilize to make a guess. This becomes a little bit granular whenever we're not understanding the other type of models. But essentially, what we're going to be looking at here will be something called softmax. So PyTorch and then softmax. So softmax is a function that I'm not going to be capable of explaining that to everybody. I apologize. But this mathematical function essentially works under the hood to try to flatten out our probability and then output a specific range out of the two. Let me see if I can break this down some more. Okay. We'll take a look at it here shortly. All right, so softmax being our activation function, meaning that in our drawing here, our activation function is what gives us a good percentage of probability so that we can choose which one of these options is more than likely true. We can make that layer by saying self dot activation layer is equal to n. Oh, hello. Totally for what it filled at. Dot softmax with dimensions being equal to 1. And now when we return our value for our features, we can just return self dot activation layer that takes in the last layer of features, which was 5. Okay, so now we can actually make an instance of this learning model. So I can say LM is equal to student, or excuse me, to learning model. Make an instance of the class itself and run it. Well, now that we ran it, how do we actually see data being fed into it? Well, we do that with our data loader. And this is where we're going to start the training process of training our model. First, we're going to build an epoch cycle, which is just essentially an iteration of how many times data is fed through the model. We will then run data through the model. We're going to talk about different learning methods, such as criterion and optimizers. And then we'll talk about how to calculate accuracy. So starting off with building, well, it's all going to fall within the same code block here. Here I'm going to go for epoch in range of 20. I'm essentially just going to do where 4 features, comma targets in my training loader. And let me make sure that's what I named it up here. Okay, training and testing loader, fantastic. All right, my training loader, which again, this is a data set, or excuse me, this is a data loader. I am simply going to feed it into my learning model. I'm going to say output, I'm going to pass it into my learning model and pass in my features. And I just want to print the output. And actually, let's do this 2 times because that might be a considerable amount of output. Okay, so there you go. I am feeding those 13 features. And from those 13 features, it is going from layer to layer, calculating weights and biases, which we haven't interacted with just yet, and then coming out with a probability. Now, as of now, it doesn't really know what it's trying to guess. I haven't started giving it any sort of direction as to, hey, this is right, this is wrong. Try to find the correct answer depending on how off you were. As of right now, it's just essentially taking in numbers and outputting numbers. And it has a bunch of default values that were created when I made those linear layers. So it's just doing its best. It's saying, all right, well, I have no guidance whatsoever. So this is what's sticking to the wall right now. Right? It's as if we just put a smear of the same glue to every single item in our pan, threw it all at the wall. This is what's sticking to the wall right now. And it's coming out with probabilities as to which one might be our best option. In this case, we're seeing that the final index came out the highest, meaning that would be our best option. All right. Well, let's actually go through the learning process, right? How could I actually learn? Well, in order to learn, first I have to calculate how wrong am I? Right? So this is called calculating loss. And in order to calculate loss, we're going to utilize a criterion. And for a multi-classification model, the criterion that's common to utilize is going to be cross entropy loss. Let's see, PyTorch, and then cross entropy loss. All right, so again, cross entropy loss takes in a ridiculous amount of information and tries to run it in the background. But essentially what it's doing is just calculating, hey, giving the input how much weights and biases are inputted, what is it exactly that we're doing wrong, right? It's calculating how off we were and at which steps we were off by. Well, how does it do this? Well, just like we described a forward step, there is such a thing as a backward step, where a backward step would then fix each one of these layers because each layer has a weights and biases. Well, in order for this backward step to take action, I have to know how wrong was each layer. So essentially, we run a comparison between our correct answer. So let's say our correct answer was here. Well, as of right now, it's telling me that this is my correct answer. So it's obviously wrong. And because it's wrong, we're going to take a look at, hey, how did you get an output of this in softmax? And then we'll say, oh, okay, well, you got this wrong because you were supposed to be at a -5. Why aren't you at a -5? And then I'll take a look at all of these tensors and figure out, oh, well, this isn't at a -5 because you were supposed to have -1. You were supposed to be +2 here. You were supposed to be at 0. And here you were supposed to be at +3. And then it's going to say, well, why are each one of these off? Well, for every single one of these neurons, it's going to go back a layer and continue this process to determine, oh, you were off by this much, and calculate each one of the loss at each one of the layers. This is called the backward step. It's not taking action. We're just calculating how off we were as of right now. Now, all these numbers eventually add up to a decimal number, and we can actually take a look at this decimal number here shortly. Oh, so again, I'm going to say from torch.nn, I want to import cross entropy loss. And I'm just going to make an instance of that. I'm going to say criterion is equal to cross entropy loss. This is going to continue to exist. I'm not going to recreate it every single time there's a new epoch. This should have a running calculator, right? So we want to put it outside of the for loop. Do not put it inside of your for loop. Well, now we could have a running loss, which is essentially saying, hey, how many times are we getting it wrong inside of the data loader? I'll set that to 0. And we could actually calculate our loss. Well, in order to calculate our loss, we would pass in criterion, pass in our output, and then pass in our label, or excuse me, our targets. And this will tell me how off was I. Let's go ahead and do this running loss here. Or let's actually activate this backward step. Yeah, let's take a look at it first. Let's do running loss plus or equals loss.item. And then finally, we could print running loss at the end of each epoch. So we run it. We see that the first loss was a 96. Our second loss was also a 96. All right. Very small difference between the two of them. And actually our loss increased, which is what we expected. Right? We continuously inspect it to increase because we have our running loss on the outside. And we also haven't changed anything. We're calculating our loss, but we're not applying the backward step. Well, the backward step applies when I call the function backward. And instead, let's do print loss.item. Well, now you can see that the loss gets smaller. Right? It was a 6-1, 6-1, then 6-0. Then it goes back to 6-1, and it's bouncing back and forth. There's a couple of 5-9s, and so on. It's having a little bit of trouble still learning. So I need to help these weights and biases be able to actually come to a good conclusion. So there's a couple more steps here. But now I'm able to apply my criterion, calculate my loss, and then, oh, I didn't call the backward function. There you go. And then call the backward function, which will actually work backwards to try to adjust my learning model at each layer so that it can continue learning. Okay, well, how can I help this model learn better? When I created all of these linear layers, they come in with default values. Well, I don't want those default values. Instead, I want to zero them all out. Da, 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 da. Oh no. Sorry, everybody. I think I lost that block of code for zeroing it out, those weights and biases. I apologize, but just keep that in mind. If you want to make your model more accurate, more faster, just zero out the weights and biases. I'll look up the block of code as additional material at the end of the lecture. All right. So that takes us into our next step, which is our optimizer. This is more on how you will learn. So the criterion calculates our loss, but our optimizer is telling our model how you're going to learn. So I'll say from torch.optim, I want to import Atom. Atom is a more common optimizer nowadays. And what this is going to take in will be our actual model parameters. So I'll just pass in lm.parameters, which is all of our weights and biases. And then I'll pass in the learning rate that I wanted to learn by, which a standard would be 001. All right, so there's my standard learning rate. There's my cross entropy loss, and I'm passing in all of my model parameters. Let's take a look at these model parameters really quick, just so that we could see them. We are starting to run out of time as well, so I will continue to move a little bit faster. Okay, so we move through these. Here it's showing me all of layer one's weight tensors and all of layer one's biases. Again, weights is how much impact it will have on the next linear layer. And the bias is the check, saying you're either weighing too little or you're weighing too much. And these are the parameters that we're passing in to our optimizer. That optimizer will help our model learn better, and I'll break that down here shortly. We can apply it inside of code now. So here we have my learning model, which I'm going to place inside of training mode now. I'm going to say learning model dot train. Going to run through a number of epochs. Here's my features. Now my optimizer, I want to make sure that it's zeroed out. So I'm going to say optimizer dot zero grad, so that it starts blank. All right, it doesn't start with any sort of biases there. It's going to start off from the very beginning with those parameters as well for my learning model. I'm going to try to make an accurate guess. I will then calculate my loss. From that loss, I'll apply the backward step, and then I'll tell my optimizer to take a step. And the step is like, think about it as in take a step towards the correct answer. Let's talk about the optimizer and how this learns. Now, the learning process here for a model looks very much like a parabola. And it's a three-dimensional parabola, which I can't really draw out here. And the best rate at which our model will learn by would be found here at its true bottom. Oh, that was the wrong marker. Now we have to tell it how to get there. Well, when it starts off, it's at 0 grad. So it's looking here. It takes a step forward at a learning rate of 0.001. Well, that might put it here. And then from there, it might realize, oh, well, there's still quite a bit of inclination. So, well, the next time I take a step forward, I'm going to take a massive step. Well, that massive step may drop it all the way on the other side. And keep in mind, we're trying to find bottoms here. If our step isn't big enough, it might fall inside of this false bottom and think that this is the correct answer. So we have to make sure that the optimizer can continuously keep climbing or taking accurate steps until it finds its true bottom. This is a lot more difficult than it sounds. And unfortunately, it's a lot of trial and error. There is some preparation and math that you can do to be able to figure this out. But for a learning model and for the purposes here in Code Platoon, this is as deep as we'll go into how to calculate the learning rate. All right, so now we have our learning rate. We're able to take a step forward. Let's go and take a look at what our running loss looks like now. Well, my running loss is starting to look a little better. I'm all the way down to 5.8 now. I see a couple of 5.6s, 5.4s, all the way down to 1.22. All right, so my loss is continuously decreasing, which is what I want. Keep in mind, this is only batches of 32, and I'm only running it twice. So I'm essentially only seeing 64 samples. And in those 64 samples, I was able to go from all the way of 1.6 for loss down to 1.22. So this is actually pretty good. My model's learning really well. Well, now let's go ahead and actually calculate some accuracy. And I think we're going to need torch metrics now. Let me see, what time is it? Yeah, let's calculate some accuracy here. Get out a code block. This code block will be for calculating accuracy. We're going to take our model into evaluation mode, take off gradients from torch, which are just basically default values. And then we'll utilize the 20% of testing data in our data loader, which I believe we call testing loader, to actually try to calculate the data or calculate our loss. Excuse me, calculate our accuracy. Now, let me go ahead and grab torch metrics really quick. I actually forgot where we installed this from. Installing torch metrics. All right, here we go. So pip install torch metrics. Nothing too tricky. We can see torch metrics has been installed. And now I can say from torch metrics, I want to import accuracy. Now the accuracy that I want to calculate will be equal to an instance of accuracy, where the task that I'm trying to accomplish is a multi-class model. The number of classes available, so the number of targets that are available will be 5. I will place my learning model into evaluation mode. And then with torch.nograd, because I don't want there to be any gradients. I'll iterate through the features and labels in the testing loader, grab my output, which again will be from my learning model, taking in the features. I'll take my predicted value, be equal to torch.max, the output.data, comma 1. This is essentially saying, hey, which one of these outputs is the highest? So probability wise, which one of them is closest to 100%? And then I'll print the prediction that was made and compare it to the label so we could see it. Finally, I'll update my accuracy with the predicted value and the true label. And at the end of it, we can see this F string here, which will show us our accuracy. I'll grab the compute dot item of this information. All right, so if I run it now, I don't expect this to do very well because I've only gone through 4 epochs, or excuse me, 2 epochs. Okay, so there seems to be an error in the way that I'm calling this. Task, multi-class, number of classes. There you go. Okay, so here's showing me a couple of outputs. We're seeing that it was expecting 1, 4, 1, 4. I'm getting 2, 4, 2, 4, 2, 4, 4, 4. So it's able to detect fours pretty well. It's having a little bit of trouble with ones or any other values. We're seeing a couple of threes that never got identified. I just realized I still have that X on my screen. And at the bottom, if I take a look, it's telling me, hey, this is only 63% accurate as of right now. All right, great. Well, that gives me a little bit of information as to how everything is running. Let me go ahead and grab my running loss. Instead of printing this loss, I'm going to simply say running loss plus or equals loss.item. I'm going to print my running loss, which is going to continuously increase. And that's this might not be the best idea. Let me go ahead and get rid of that portion. I'm going to increase my number of epochs here all the way up to 20. Again, this is learning. Let me actually restart my entire kernel. I'm going to run all from top to bottom. What's happening now? Oh no, we were just past this. And of course that would fail. Oh, I apologize, everybody. We were doing so well. All right. Well, currently right now it is 11:03. Let's go ahead and take a 10-minute break. When we come back, I'll do a quick 5 minutes over the end portion of the lecture, and then after that, we'll dive into our retro. Thank you so much, everyone, and I'll see everybody back in 10. All right, welcome back, everyone. So just quickly, the mistake that happened up above, again, in our tensor data sets, when we were creating them, I had to turn this back into an NumPy. So I execute this, and now What are we getting? No object to numpy. That's funny. Okay, so I take that off. Now it's able to execute. Seems to be bouncing back and forth. I'll have to do a little bit of digging to figure out why that's happening. Come down below. Everything else is working correctly. I go into the training of our model. I'm running it through 20 epochs. As I run it, we can see our loss go all the way down to 0.9, 0.2, bouncing back and forth. And it seems like our last loss was at 1.01, but the fact that it's down to 0.94 gives me a pretty good feeling. If I run it for accuracy, we can see that now my model is 86% accurate. Right? So that was the difference of just increasing the number of epochs that it's going through. It's going through 20 epochs now. If I were to increase this to, let's say, even 100, well, at that point, it may become too repetitive because I don't have that much data. All right, so 32 times 100, it would be going through data 32 or 3,200 times. It went through those 3,200 times in 5.8 seconds. Its output really wasn't much different. All right, we're down to zero point 0.9, but it wasn't a drastic difference like I expected. Well, if I take a look at the accuracy now, it's only up to 87%. I only increased my percentage that I learned by 1%. Why could that be? What might have happened when I trained my model so much with the same data? Let's hear it, Chris.
Is that due with the overfitting?
Yeah, I actually started overtrain. I actually started training. Oh, excuse me. I actually started teaching my model how to memorize information rather than recognize pattern. Right. So I gave it the data, same data over and over again to the point where it just started memorizing. All right. So because we don't want it to memorize, keep it to a low epoch number. 20 epochs is usually a pretty good range. If you need to go anything above 20 epochs, I would say 100, definitely your cutoff. But keep in mind the amount of data that you really have, right? Because if we take a look at our total number of entries, we only have 3,392, right? If I go through this 100 times, that would be 3,200. And keep in mind, I'm only working with 80% of that data, which who knows what that is. Let me see. Calculator. Let's do 3,339 times zero point 0.8. So I only have 2,671 possible entries that's actually being learned there. And I have 32 batches that are already passing in. So I'm going through the same batch 83 times. Or excuse me, there's only 83 possible batches that I can work with inside of each one of those epochs. So if I'm going over 100 epochs, that means 27 times it utilized repetitive data, right? Not something that we want there. All right, go ahead, Rick.
Yes, is this the most intensive part of it? It sounds to me like, like however many epochs you put, your computer, your laptop, your CPU or whatever has to go through it, however many times you do like the epoch. Is this like where, the your hardware come starts to come into play?
Yes, this is essentially the part where a high part of your computer power will be utilized. All right. Now, this is it as far as today. I would like to encourage everybody while you're working on the material today to take a look at optimizers, how they work, criterions, how they work, And when it comes to building your model, take a look at the ReLU function and take a look at dropout layers to increase your model's ability to make accurate predictions. All right, so today we covered how deep learn what deep learning is. We covered pre-processing data with pandas, how to account for null, grabbing our features and labels. We went over how to standardize our data, converting our data into a training and test split, where we had 80% training and 20% testing, turning those into tensors, feeding them into tensor data sets that were then introduced into tensor data, into data loaders. We then created a learning model utilizing PyTorch. This is a multi-classification learning model. By establishing both the init method and the forward pass, we took a look at those parameters of weights and biases. We then trained our model utilizing cross-entropy loss and Atom, and calculated our accuracy with torch metrics for the accuracy class. At this point, does anyone have any questions over the material that we covered today? Let's hear it, Chris.
Did you ever find that was it that block of code for the zero out what was it? I think it was before the optimization.
The zeroing out weights and biases, I have to look that up and then I'll pass it out inside of the Slack channel.
Okay. And then I had another question. So it looks like, is it batch size, learning rate, layers, and epochs? Like those are the only. I mean, I'm sure if I played around with different numbers, that could affect the overall accuracy.
Yes, that's right. So if you play with those numbers, it will affect the overall accuracy, specifically because the batch size and the I think we specified it in the testing size as well. Essentially, when it comes to chunking, the smaller amount of numbers, the more randomness there is. The higher amount of numbers, the less randomness there is, right? The standard is 42 and 32 for those two. Now, if let's say I decrease it and I go to something like 16, well, that would become so random that might be harder for your model to learn, right? Because input is so random that it can't create relationships. Now, let's say I increase it and instead of going for 16, I go for 64, right? Increase, so 32 times 2, I go for 64. Well, now there's not enough randomness. And instead of learning to recognize patterns, it's memorizing. Does that answer your question, Chris?
Yeah, and then with the layers, like, is there? I saw you only put what, like 5 layers. Is that because I'm assuming that's the amount of targets you have?
No, so actually the amount of layers is completely up to you, how many layers you have. It kind of depends on the design that you want to go with. The way I like to think about layers is I want to create a diamond where information comes in. Oh, let me see if I could do this. And gets dramatically increased at the very beginning and then slowly decreased towards the right-hand side. All right, we could have made 6 layers if we wanted to, 7 layers. You don't want to have too many layers because then they would have a dependency upon one another where the relationships would be too strong and it might be harder for your model to learn. But you also don't want to have too little layers because then the connections may not be strong enough. And to measure it out as far as like what's the best thing, I would say stay between 3 to 6. Anything above 3, anything above 6, that would be overkill. And anything below 3 wouldn't be meaningful enough to actually create accurate depictions.
Awesome.
All
Thank you.
right. Tom?
To kind of piggyback off of his question, um, for the batch sizes, is there any tools, or is it just bad practice? But would you be able to start off at a higher batch size to establish relationships and then drop it down more dramatically to start introducing more randomness to effectively increase its accuracy capability?
You could do that. Absolutely. You could start off with a couple. I think at that point you're getting into a lot of the fine stuff when it comes to being able to train a model. If you're training an entire neural network with a brand new purpose on your own and there's a tremendous amount of data, you could definitely do that. But again, you would need a tremendous amount of data for that. All right. Any other questions, Tom?
Nope, that was it.
All right, fantastic. Any questions to class? All right, if there aren't any other questions, I'm going to go ahead and stop our recording here.